Hello everyone, my name is Tian from University of Massachusetts Amherst. Today I'm going to present my work called Distributed Framework for Accelerating Training of Deep Learning Models through Prioritization. As we know, the machine learning has been successfully used in many fields. Our daily life has been deeply affected by machine learning. For example, when you wake up in the morning, you pick up your phone and say, "Hey Siri, what's the weather today?" Your phone will tell you the weather using a speech recognition model to understand your question. Then you leave your home. On the way to your work, you see a beautiful flower. You take a picture and Google will tell you the name of the flower using a computing vision model about object detection. At night, after a day of hard working, you just want to play some games. But you may not know some of your teammates and rivals are not human. They're just some AI agents. But training machine learning models are getting harder and harder in recent years. There are two major reasons for this problem. First, to address the complex real-world problem, people are designing bigger models. Second, in order to train these bigger models, people collect the larger data sets for them. For example, in 1998, people create a data set of handwritten digitals containing 70,000 images and can train a model with 99% of accuracy with only 1 million of parameters. But in recent years, people are using millions of images to train the network for object detection and face recognition. And the number of parameters in these networks grows about 100 times. Gradient descent is one of the most widely used algorithms for training machine learning models. It decreases the loss function L of W by tuning the model parameter W with its gradient. Usually, the loss function is accumulative. It means that the loss of W over a dataset can be computed as the summation of L on each data point. Here we show an example containing 4 data points. We can compute the gradient of each data point using G1, G2, and G3. After computing the gradient of each one, we sum them together into the total gradient G and update the model parameter W with the aggregated gradient G. Since the gradient of each data point is different, we guess that maybe the contribution of them to the loss function is also different. So we quantify the contribution to the loss function of a data point di as how much the loss function changes if we only update the model parameter with di. We can compute the changes of the loss function using calculus. We can approximate with the gradient of L over W multiplies the delta of W. Since we assume that only di is used to update the model parameter, so the delta W is eta multiplies the gradient of I. Therefore, we can compute the contribution of a data point di as eta multiplies the total gradient of all data points multiplies the gradient of data point I. We examine some machine learning models with the contribution metric, and we find that the contribution of different data point can be significantly different. For example, here we show the contribution of the top N% of data point for a logistic regression. So here we can see in iteration 1, the top 1% of data point contribute about 10% of the changes of the loss function, and the top 5% of data point contribute about 50% of the changes of the loss function. As we know, that the most time-consuming part in training a machine learning model is computing the gradients. By finding this phenomenon, we can use a very small portion of gradient to get most of the contribution. So this will save us a lot of time during the training process. So that we get an idea, but why don't we just train on the most valuable data points? But there are two challenges that prevent us from doing this. First, the most valuable data points are not static. They change over time. As we know, the model parameter changes over the training process. It means the gradient of each data point change over time. As a result, the contribution also changes over time, and the value is not static. Second, finding the most valuable data point is time-consuming. According to the discussion in previous slides, we know that the contribution of a data point is computed from the gradient of that data point. But computing the gradient of a data point is the most time-consuming part during the training process. We want to speed up the training process by avoiding some gradient computation, so that we need to have some method that can give us the contribution of a data point without computing the data point's gradient. So here we propose a prioritized gradient descent system, which is able to compute the gradient of each data point for all iterations. And we propose a method that is able to give us the contribution of the data point efficiently without computing their gradient every time. So compared to the typical mini-batch gradient descent algorithm, our prioritized gradient descent algorithm computes the priority of each data point in each iteration, and then we select the mini-batch as the top k data points. So estimating the priorities of all data points is the key part of our PGD system. So we got two major ideas for estimating priorities. First, we learn the priority trend from their history for each data point. As we know, in gradient descent algorithm, we usually use a small learning rate to prevent the model parameters from moving too fast. Therefore, the model parameters changes gradually across iterations. Therefore, the gradient of each data point also changes gradually. So for the contribution of each data point, which is computed from the gradient, also changes gradually. So we capture the gradual changing trend of the priority value with a small model, and we learn this model using the history of the priority values, which is computed from the real data. And then when we want to use the priority value, we just predict the priority value using the model. Since the priority estimation is a very frequent task in the PGD algorithm, we should use a lightweight model to learn and predict the priority, so that we can minimize the overhead of PGD system. and the priority doesn't change drastically. Our evaluation shows that a small model with only three parameters is good enough to capture the priority trend with periodical renewal. The second major idea to estimate the priorities is to periodically renew the learned models. There are two reasons for us to periodically renew the learned models. First, by doing this, we are able to keep the learned model up to date. Therefore, we can get the more accurate estimation of the priorities so that the selection of the target data point will be more accurate and we will have a faster training speed. Second, it improves the quality of the final result of the training process. During the periodical renewal, we scan all the data points fairly. For each data point, we compute its gradient and priority to update its priority prediction model. The gradient computed here can be used with the gradient from the target data points together to update the model parameter. This ensures that the training process uses every data point in the dataset, so that it prevents PGD from selecting a biased subset of the dataset. As a result, it prevents PGD from falling into a local optimal and have a higher chance to find the global optimal. You can find more detail about estimating priorities in our paper. We evaluate our PGD system with three machine learning models: the logistic regression, multi-layer perception, and convolutional neural network. We use both synthesized data and real-world data to evaluate our system. For the real-world dataset, we use the MNIST dataset to test the MLP and the Tian model. We implement our system using C++ together with the OpenMP library. You can find the implementation of our code at GitHub. First, we compare the conversion speed of our prioritized gradient descent system with the mini-batch gradient descent algorithm. We do the evaluation on both MLP model and the Tian model for the MNIST dataset. As we can see in the figure, for both the MLP model and Tian model, our PGD system converges faster than the SGD algorithm. As we can see from the figure, PGD outperforms SGD much more at the beginning of the training process. This is consistent with the distribution of delta L contribution we showed in previous slides. As the training process goes, the model parameter will be moved to a balanced position among all data points, and then the most valuable data points will not contribute as much as they were at the beginning of the training process. In this slide, we show how the priority estimation of SGD affects the training results. Here we conduct an experiment on the logistic regression model. We train the model for the same number of iterations using different renewal ratio, which controls how much data point gets renewed in each iteration. As we can see from the left figure, if we don't renew or just renew a small portion of data points, the final training result may not converge. And with the increase of the renewal ratio, the final loss of the trained model will be lower at the cost of a longer training time. For the experiments shown in the right figure, we select a large number of top data points in each iteration. As we can see, the lost not bump as the left figure. It is because the top visual is large enough to prevent their average gradient from being a random direction. But even for this case, if we don't do the renewal as indicated by the blue line, the loss function also does not converge. So therefore, the periodical renewal of PHAD is critical. It is able to prevent the divergence and improve the quality of the training results. We designed the prioritized gradient descent system as a distributed training system, so we tested the scalability in this slide. Here we demonstrate the scalability testing results over the CE model on the MNST dataset. We implemented both the synchronized version and the asynchronized version of PGD. As shown in the figure, for both versions, the PGD system scaled linearly with the increasing number of workers. And as we can see in the right figure, the asynchronized version of PGD scales better than the synchronized version. Here we conclude our work. There are three takeouts in this presentation. First, we propose a prioritized gradient descent system, which is able to accelerate the training of many machine learning models. Second, our idea is to identify the most valuable data points during the training process and train the model with these most valuable data points. Third, from the perspective of techniques, we propose a method that is able to efficiently estimate the contribution of each data point without computing their actual gradient. And this method is able to give us the contribution of data points during the whole training process. Thank you for listening. If you are interested in our work, please check our paper for more detail. Thank you.